Good evening and welcome to the second workshop in the Groundwater University Workshop Series. And welcome back if you've attended the Groundwater U listening session in January or the first workshop held in February, or if you've reviewed the video recordings that are on our webpage. My name is Jamie Slaughter, and I'm the Public Participation and Community Outreach Manager for SSFL at DTSC and will be facilitating this meeting. Thank you for participating tonight. The Department of Toxic Substances Control's mission is to protect California's people, communities, and environment from toxic substances, to enhance economic vitality by restoring contaminated land, and to compel manufacturers to make safer consumer products. As a reminder, this educational workshop series is designed to prepare interested stakeholders for upcoming groundwater decision documents and associated public meetings and comment periods. The agenda for this meeting includes an overview and purpose of the workshop, followed by a presentation about where groundwater contamination is at SSFL, the Chatsworth Formation, and the fate and transport of contaminants. Then we will open the meeting for a discussion and question and answer, followed by dates for anticipated upcoming groundwater decision documents and associated public comment periods, and closing with ways to stay connected. Tonight, we ask that you please be courteous to all meeting attendees, and this meeting is being recorded, and you may be muted if necessary. When providing input or asking questions verbally, please speak clearly and at an even pace. Each participant will have 2 minutes to ask your question. You may also type questions or input into the Q&A section throughout the meeting. The Santa Susana Field Laboratory consists of 4 administrative areas used for research, development, and test operations, as well as undeveloped buffer areas. The Boeing Company, Boeing, the U.S. Department of Energy, DOE, and the National Aeronautics and Space Administration, NASA, are identified as the 3 responsible parties, or RPs, for the site. This slide clearly defines the responsible parties' administrative areas for soil cleanup. However, there is some overlap and shared responsibility for groundwater cleanup. For example, between Boeing and DOE in Area 4. Now we will transition to the workshop presentation for this evening.
Welcome, everybody. Good evening. My name is Mike Bauer. I am the Santa Susana Field Laboratory, or SSFL, Remediation Program Manager for the Boeing Company. I am pleased to help facilitate tonight's presentation titled, Where is Groundwater Contamination at SSFL, the Chatsworth Formation, Fate and Transport of Contaminants. Just a bit of background on myself and some of the other Boeing team members that will serve as panelists for tonight's presentation. I have a bachelor's and master's degrees in geophysical engineering, as well as a master's degree in geological engineering, all from the Colorado School of Mines. I recently studied in all my spare time for a PhD in engineering under Dr. Beth Parker at the University of Guelph, and that effort is currently on hold. I'm a registered civil engineer in the state of California, and I have over 30 years experience managing soil and groundwater cleanup projects. I am also a Boeing Associate Technical Fellow, which is a highly selective technical leadership group, and I am a Boeing designated expert in remediation technologies. With me on the panel tonight is Mr. Richard Anderchek, who is an engineer and senior technologist for this consulting company, Stantec. Rich has been working on this project for a couple of decades now, collaborating with the Groundwater Advisory Panel on many aspects of the groundwater investigation. Rich was the primary author of the draft groundwater investigation report that was published in 2009, a document that was written for Boeing, DOE, and NASA that included the entire site. Since that time, Rich has continued to update the investigation reports for the Boeing areas of responsibility, including being the primary author of Boeing's final groundwater investigation report, which was approved by DTSC in 2022. Rich is also the lead author of Boeing's groundwater corrective measure study report that will be submitted to DTSC in June of this year. Rich probably knows more about the site history and operations related to groundwater impacts at SSFL than anyone I know. Also assisting on the panel tonight is Dr. Fernando Mana, Assistant Professor at the University of Guelph in Ontario, Canada. Dr. Mana was hired several years ago to do postgraduate work under Dr. Beth Parker and his research focused on infiltration and groundwater recharge at SSFL. Dr. Manna has published several peer-reviewed journal articles on the nature of groundwater recharge at SSFL, questions around which have arisen in the previous Groundwater U sessions. Finally, just a word about the presentation you will see tonight. We are fortunate to have as presenters Dr. Beth Parker, professor at the University of Guelph and a Canadian Industrial Research Chair, and Dr. John Cherry, distinguished professor emeritus at the University of Waterloo and adjunct professor at the University of Guelph. Doctors Parker and Cherry, along with Dr. David McWhorter from the Colorado State University, who's now retired, formed the Groundwater Advisory Panel in 1996. Much of the science behind what our industry knows about how contaminants move through fractured sandstone, like we have here at Santa Susana, has been advanced by this advisory panel. They have worked collaboratively for and with the other RPs, for example, site-wide investigation and conceptual model site reports in 2009, but they have been focusing their efforts on the Boeing areas of responsibilities for the past decade or so. As such, some of the material presented tonight will show groundwater plumes and associated information from Boeing's areas of responsibility. However, the science and information presented on the transport and the fate of groundwater contamination tonight is applicable to all parts of the Santa Susana site. With that, I am pleased to turn the presentation over to Dr. Beth Parker and Dr. John Cherry. Thank you.
Thank you for joining this evening. John Cherry and I join you from the University of Guelph here in Ontario, Canada. And I look forward to talking to you about groundwater contamination at SSFL and in general, how contaminants behave in fractured sedimentary rock. This view just introduces us as full-time faculty as university professors, where we've dedicated our careers toward teaching and performing research and mentoring graduate students.
Well, good evening, everyone. So I started off my undergraduate degree at the University of Saskatchewan. It's very cold there, so I decided to escape and do a master's degree at Berkeley. Spent a couple of years at Berkeley, wonderful weather, but found the weather boring. So then I went to Illinois and did my PhD for a couple of years. And then I craved cold weather, so I went back to Canada and ended up at the University of Waterloo. And in the midst of all of this, I did a postdoc in France. In 1979, I published a book with a colleague, Al Fries, at the University of British Columbia. And in fact, some of the science in that book is what was done early on in this study that we'll report on today. In 1988, I established the University Consortium for Solvents and Groundwater, which is continuing to this day, and which we reported on the Santa Susana project almost every year then for more than 30 years. I'll turn it back to Beth.
Okay. Starting a couple decades after John, I started out in New York. I was born and raised in Western New York and did most of my education on the East Coast of the United States, and found my first full-time job or real job at Eastman Kodak in Rochester, New York. And that's where those photographs on this slide are from. In the mid-1980s, I was introduced to organic solvents and how mobile these contaminants were, especially in fractured rock, which is what I was working with there. And so we were busy drilling boreholes and installing wells and discovering the impacts of organic solvent operations at an aged manufacturing facility. And it was the complications of this type of contamination that introduced me to John Cherry and Dave McWhorter, first as my advisory panel at Eastman Kodak, but later as my supervisors as I went to the University of Waterloo to get a PhD. And after I finished my PhD, I stayed as a university professor, first at Waterloo and then at the University of Guelph, where I continued to conduct research and supervise graduate students. So I thought we should start off just by clarifying some terminology. We use the term DNAPL to represent organic solvents like TCE, which is what we'll be talking quite a bit about today. as it's a dense non-aqueous phase liquid, and that's because as an organic solvent, it's only sparingly soluble in water. So the photograph we see here are red dyed TCE in the solvent phase, immiscible with the clear water that it shares in that glass container. Dense non-aqueous phase liquids means they're denser than water, and they're also known to be have low viscosity, which means that they're going to move very quickly in the subsurface, but they're sufficiently soluble in water that they create fairly large plumes. So as part of my PhD, I discovered the importance of diffusion on the influence of DNAPL complete dissolution in fractured rocks, such as sandstones. And part of that came from observations at my Kodak days and thinking about some of the science that was in the book Freeze and Cherry. But what I presented and published as part of my PhD is the new idea that the DNAPL that is highly mobile in the fracture network will exhibit a large surface area to volume ratio, which means it'll completely dissolve away very quickly. And so we evolved from the condition on the left, which is an early time condition, to the condition on the right, where all the mass has left the solvent phase and dissolved and diffused into the matrix, the low permeability blocks of rock between the fractures here. And this idea was actually a new idea presented at a professional short course that John Cherry, Dave McWhorter, and myself were involved in teaching in the early 1990s. And an engineer from Rocketdyne was in the audience taking the course, and he was reasonably impressed by how this conceptual model that I was presenting in these lectures might be relevant to the Santa Susana Field Laboratory. So from there, all three of us were invited up to the site, and we became part of the Groundwater Advisory Panel established by Rocketdyne in 1996. And this is a view of the three of us in 2011 when we gave an overview of the science that as we understood it at that time, nearly 15 years ago. So today's discussion here is about refinements in our understanding based on lots of work that's happened by consultants, by all of the RPs at the site here today, as Mike has mentioned. But before I get into the site in specific detail, I thought I would give an overview of the types of research that both John Cherry and myself and Dave McWhorter have performed over the decades. And these blue dots and red dots represent all of the sites where we've done research, field research, where we take our graduate students and staff and collect novel data sets to help understand the processes that are happening in the subsurface. So the red dots represent the 4 sedimentary rock sites that I've made a key part of my sedimentary rock research program that Mike Bauer has mentioned. And as you can see, Santa Susana is one of those 4 sites, the other 2 being closer to the Great Lakes, and 2 of them very close to home here near Guelph, Ontario. And just in a quick summary, these sites are similar and distinct from each other in important ways to help inform the science. So here at the top, we have the California sandstone shale, and it's an interbedded fine-grained sedimentary rock that has been faulted and thrusted, and so the beds are dipping slightly off of horizontal. And we also are existing here in Southern California in a semi-arid climate. In contrast, the 2 sites in Ontario and the sites in Wisconsin have quite a bit more rainfall, and the sedimentary rocks are horizontally bedded in their natural state that we're working with today. But it's important to note that all types of hydrogeology are fit into 5 or so major classes. To distinguish how contaminants behave in each of them is quite distinct. So the U.S. National Research Council has kind of put these 5 categories together, and Santa Susana and those 4 sites that I was just talking about fit into the category 5 as fractured porous media or fractured sedimentary rock. And these contrast with more common aquifer types that we're familiar with, which would be sand and gravel aquifers. What we see on the left is a view of sand, and the permeability of the sand is the pore space between the individual grains of sand, and that's what allows the groundwater to move through that aquifer type. In fractured rock, it's the fractures that allow bulk fluid movement or water to move through this system. And so it's the discrete fractures that are connected to each other that are conveying the groundwater. And yet there's blocks of rock between the fractures that are porous, but not very permeable. So they don't contribute so much to the bulk fluid movement, but there's a lot of void volume or storage volume for dissolved mass to move into that space. So we've mapped the plumes at these 4 sites, and you can see the Santa Susana plume in the northeast near the front gate at the property. So it's only one portion of the site that we're showing in detail at Santa Susana in the upper left. And then, but the largest plume of the 4 plumes is the Wisconsin site plume, and it's about 2 miles in length away from the Dean Apple area. And the smallest plume is the Guelph area site, and that's less than a half a mile in its length. Anyway, this brings us to a paradox that we have rapid flow in the fractures in a fractured rock aquifer, and yet we see evidence of very slow moving plumes where the mass or the contaminant plume hasn't moved very far from the input locations. So today we'd like to talk about some of the reasons why that's the case. And what we emphasize in our investigation work, not only in our research, but our professional colleagues that are engaged in this type of work at sites, is we work at multiple scales. And what's important about understanding the middle scale, the plume scale, in terms of where these plumes are heading and how fast they might be migrating toward those receptors, is to understand the processes at the fracture scale. So and on top of that, we need to understand the groundwater flow system. So I'll talk about the contaminant details, and then John's going to give us the context by talking about the flow system scale a little bit later this evening. In 2011, we presented this cartoon sketch as a representation of the contaminant distributions at the Santa Susana Field Lab. So we have a vertical exaggeration to kind of see the topographic high that the site sits on. And we are illustrating rainfall is the mechanism for recharge to the groundwater table that's not very deep below the ground surface. But most importantly, what we're showing is the TCE plume in red, or the perchlorate or tritium style plumes that we show in turquoise and purple, are more or less constrained to within the property boundary. And that's because of the mechanisms that are happening at the site, coupled with the rates of recharge and groundwater flow, and all of these things working interactively in a particular way. So those are the things we'll talk about here. So we were introduced to the site in 1996 with our first site visit. Soon after, I had a graduate student arrive at the site, bringing some of the new ideas for data collection to Santa Susana. And we presented a lot of that work that culminated in a draft RFI report submitted in 2009. And so that's the 2011 Groundwater U. What we want to focus on are the things that we've learned since 2011. There's been a number of studies, including a SEEPS report, a fault study report, a calibrated and validated flow model report. And now the group is working, various groups are working on corrective measure studies that will be submitted within the next few months. And our goal here is to talk about the contamination in a way that allows the public to engage in the public comment period effectively. So I'll move right on to Santa Susana. And this is the way we got introduced to the site. We entered the site from Chatsworth, so we're driving down Plummer Street, and we can see the Chatsworth Formation exposed in the Simi Hills as we're driving up this mountain, arriving at the front gate for the first time. And we were, I suppose, a little bit nervous as to what we might be getting into here, because it certainly looked complex on our first view. In a Google Earth view, we can see the outline of the Santa Susana Field Laboratory. It's 2,850 acres in aerial extent, and we can see its position in the context of the Simi Valley to the northwest, and the West Hills and San Fernando Valley to the east. And this slide is really just showing the distribution of the different rock formations, and you can see that the majority of the site is sitting on the Chatsworth Formation sandstone, and all of the operable units on the property are on the sandstone. So starting with the insert in the upper left, we can see we have a cross-section drawn from AA prime that extends from Simi to San Fernando Valley, and that gives us a vertical cross-section view of the site that's sketched here, showing all the different rocks kind of layered on top of each other, but thrust upward because we're in a tectonically active area. And it gives you a sense of the topographic high relative to the valleys to the sides. But note that this is vertically exaggerated by a factor of 10. So it is a distorted view of things, but it does give us a chance to kind of see the faults and the structures. It gives us a sense of groundwater recharging on the topographic high and how it's going to create the driving force for groundwater movement from the water table on site toward the seeps on the sides of the hill slopes and down into the valleys beside the site. But here's a more realistic view of the site in terms of the topography and the position of the site relative to the valleys. Here's a view of the Chatsworth Formation as we're driving up Bullseye Canyon Road, and we can see the blocky structure created by the fractures and the matrix blocks between those fractures. We get a sense of the bedding. This is another view that shows the variable thickness of the beds. Some are thicker and some are thinner, and the tilting of those beds is about 30 degrees from the horizontal. And some of the inserts here show the scale of this bedding and the nature of the vertical joints that are intersecting bedding plane fractures that create the interconnected network of fractures for groundwater flow. It's important to note that there's two types of porosity that makes up sedimentary rocks. The void space due to the presence of fractures, and the void space that's associated with the individual grains of sand or silt, or what we call the primary porosity or the matrix porosity. And what's really important to I guess, acknowledge here is that the fracture porosity tends to be a very, very small number compared to the matrix porosity, even though the fractures are what are the paths for groundwater movement. Another set of terms here, the water table exists about 80 feet below ground surface throughout much of the site, and that leaves an unsaturated zone from ground surface down to the water table. And that unsaturated zone has fractures and matrix pore space filled with both air and water. And below the water table, it's completely filled with groundwater. And we'll be talking about the groundwater contamination below the water table here tonight. So this cartoon view of the site in cross-section with this vertical exaggeration shows that the water table is not far below ground surface, and we have a strong downward gradient for groundwater movement down and out to the sides of the hill slopes, as well as to the valleys below. So what are the contaminants we're dealing with at the site? The primary functions that operated at the site for the last 70 years involved rocket engine testing for NASA and nuclear and liquid metal research for the Department of Energy. These operations started in the late 1940s and in the 50s, and the bulk of the activity was in the first 10 or 20 years, and then subsided, or much less activity happened in the later decades, with all operations stopping in 2006. The rocket engine test stands are a key place where the trichloroethylene, or TCE, was being used. And after a rocket engine test was completed, TCE was used to clean out the combustion chamber, and the TCE as solvent, as well as the water phase, would drain into these retention ponds nearby. And it's our expectation that at some of these locations, solvent as NAPL or DNAPL would have gotten into the fractures in the rock and migrate deep below. So let's focus on the right-hand map. We can see the different responsible parties here coded in 3 distinct colors. So the green is the Boeing operations, blue is NASA, and brown is DOE. The culmination of the RECRA facility investigation report submitted in 2021 shows there's 16 mappable contaminant plumes in the groundwater at the Santa Susana Field Laboratory. And we can see that a number of these are organic solvents, and TCE is the most prominent one that we've been seeing in our monitoring wells. So how did these contaminants get into the ground? We've already talked about the rocket engine testing, which is shown on the left, where solvent NAPL is migrating deep into the subsurface because of its density following along the fracture network. In contrast, we have some powders and solids that would have accumulated at ground surface, but would recharge with the rainwater that infiltrates into the subsurface, getting to the water table and creating a dissolved phase plume. And also there's wastewater containing solutes that would have been discharged at the site, contributing to groundwater chemistry. So we'll focus quite a bit on TCE, and this is a cartoon that gives us a distinction of particular zones in the subsurface. TCE going in as the NAPL phase is referred to as a subsurface source zone. The groundwater that moves through that source zone is picking up dissolved phase constituents and carrying it in the groundwater. That's the plume. And then at the leading edge of the plume, we refer to that as a plume front. And the position of the plume front is something that we pay attention to, as well as the concentrations internal to the plume that we'll be monitoring and showing some results for. I've emphasized TCE in our investigation work as the most mobile contaminant of all of those that we saw on the list. And that's partly because of the DNAPL stage of the contamination problem, when it can move very quickly down these fractures. What we see in these individual fracture pathways here is a diffusion halo away from the fracture, and that's due to diffusion in the aqueous phase. So it's another process that strongly impacts the forward rate of the plume migration in the fracture, as you can see by the different distances that these solutes have moved in these scenarios. We monitor with conventional wells that are paired or in triplets. We call monitoring well clusters. And then in the last 20 years, we've been installing engineered multi-level monitoring systems, and they can have numerous ports with seals between them to allow us to do vertical profile sampling and inform the 3-dimensional details. Since 2011, we've added an additional 159 wells. So we have more than 618 well locations across the site and more than 1,000 groundwater sampling ports. And this is what helps to inform these maps that are being prepared, where we have outlines of the plumes, the contaminated zones for 3 constituents of that list that we showed earlier. So TCE is the green, perchlorate and tritium are the other 2 examples here. What I wanted to show here first is the temporal or time varying conditions for the mappable TCE contamination. So what we have are 3 maps, 3 different time periods from the 1990 decade, the early 2000s to mid 2015 period, and then the last 7 years. And at a broad view, we can see that the outlines of these plumes or these footprints are nearly the same. And it really takes a more careful look at the internal concentrations to see how things are evolving with time. So releases have stopped occurring. And so what's happening is we see that the plumes aren't migrating in a noticeable distance, but the concentrations internal to the plume are diminishing over this 30, 40-year period of time. If we take a particular look at an individual well, this is the type of data we would see. So on the map, you can see that I've circled the location that RD1 is situated here in area 1. And what we have for RD1 is concentration in micrograms per liter in the groundwater for TCE and the degradation products of TCE that are common in groundwater systems. And the solid dots represent measurable, quantifiable concentrations with time. The lower plot represents the position of the water level in the well that we're taking these samples from. And you can see that there's a period of pumping of RD1 and a period of non-pumping, and more recently starting pumping again. And you can see how the changing of the hydraulic conditions in the well or on the site might have an influence on concentrations versus time. This is just a cartoon to show how TCE loses a chlorine to convert to successive what we call daughter products or degradation products. And these contaminants essentially are associated with each other. And the photos at the bottom represent the nature of the minerals in the Chatsworth Formation that provides some reactivity that helps to destroy these contaminants naturally in the Chatsworth Formation. Now I just want to show you how these parent and daughter products, or these chain of contaminants that are related to each other through this degradation reaction, are co-located at the site. So again, we're still in area 1. This is the mappable equivalent TCE. So the sum of TCE and all the degradation products added together is shown on the left, with internal concentrations varying by orders of magnitude. On the right, we have TCE by itself. And they're very similar to the total equivalent TCE that's shown on the left. The cis TCE is remarkably smaller in area footprint, but not outside of the TCE footprint or the equivalent TCE footprint. And that's true for the vinyl chloride as well. So the bulk of the TCE mass remains as TCE or cis TCE. Another aspect of the contaminant situation is thinking about the position of the contaminants in the context of the direction of groundwater flow. Now, this is a very complex, fractured, faulted system with these layers of rock that vary in permeability and fracture characteristics. And so what we see here are 4 blue arrows representing 4 different flow trajectories away from a single operational area, what we would call a single source area, where TCE would have gotten into the ground. And because it's a 3-dimensional problem, the light blue arrow sits on top of the medium blue arrow, and we can see some of these arrows are migrating preferentially along some of the fault structures that are part of the interconnected fracture network at the site. In summary, there's a whole bunch of processes working interactively. We've got the advection of the groundwater flow in the fracture network that's also contributing to what we call dispersion. Diffusion is happening away from the fractures, so you can see that as a diffusion halo, and that has a strong attenuation effect. And then we have sorption and reactions happening in the matrix as well. So I wanted to show you how this plume would have evolved over the past 70 years. And to do that, we have to use our understanding of those processes that I've just talked about, and then use numerical models to simulate this behavior through time. So here we've got a 300 meter by 1,000 meter domain. You can see the statistically generated fracture network. We test the realistic nature of that by comparing that to our measured bulk hydraulic conductivity at the site from pumping tests. And we know the matrix and fracture network properties as well as one can. And we're going to look at dissolved TCE coming in with the groundwater on the left-hand side of the domain, moving toward the lower right. So the next slide here, I want you to focus on the larger domain, the 300 by 1,000 meter domain, to see how this plume is going to evolve over the next 70 years. And it's going to step through time in 5-year increments. And then the insert is just allowing you to see in more detail how diffusion causes spreading from the fractures into the center of the matrix. So you can see the decade time marching through in the upper right-hand corner. The concentrations are varying over 6 orders of magnitude. So each color represents a distinct order of magnitude. And we're going to end at 2020 as our modern condition. What we see is we start out with orange and bright or warm concentrations near the source, and over the first 30 years or so, that orange color diminishes. I'm repeating this simulation again for the sake of catching some of the finer details. So the orange is going to start to diminish in the 80s and 90s here. And that's because of this transverse diffusion into the matrix blocks between the fractures. And the front of the plume slows down dramatically. You hardly saw it move after the last 20 years or so. I'm moving on here. And in summary, we have a few cartoons that kind of show this stages of development. Most of the TCE was used in the 1950s because of lots of rocket engine testing in that decade. We have NAPL getting into the fractured rock, and the groundwater moving through that NAPL is creating a plume in the down gradient direction. So we can see here that after we stop spilling a lot of TCE, that some of the NAPL that already made it into the fractures is going to dissolve away, as we previously talked about, but that dissolved mass is going to move in the direction of groundwater flow, continuing to expand the plume. In stage 4, the plume continues to expand, but the rate at which it expands is getting much, much slower, to the point where it almost appears to be at a steady state position. This is what we seem to see here at the Santa Susana Field Laboratory at the current point in time. What's going to happen in the future? We see evidence at other sites, the other 3 sites have been studying, that the continued diffusion and reactions in the matrix are causing the contaminant mass out at the leading edge to completely degrade away to non-detect values, and it gives the appearance that the plume front is retreating back to closer to the source zone. And if we give it a long enough time, this retreat continues, and the plume essentially shrinks in on itself and completely attenuates. The question is, how long would that take? And our numerical model gives us some insights to that by forecasting the future decades. And I don't have a video here, but I'm showing 3 time snapshots that take us 125 years into the future. We see that it reaches its maximum extent in 2050, and we see that the plume front is starting to appear to shrink back toward the upper left-hand corner in 2100 and 2150. How well does this model represent reality? Well, remember, I've informed it with a whole bunch of parameters that were derived from measurements in the field and in the lab to simulate those conditions. But we can also test the output and look at what the characteristics of the plume are like by studying it in more detail. I've been using continuous cores through the contaminated zone. The cores are brought to surface and we log the cores and sample near and away from the fractures that are identified in the core. And that gives us a concentration with depth profile. And we find the mass in these diffusion halos adjacent to fractures that once contained the napple or the plume in the fractures. This is a view of the drilling at the site where my students were involved in the field. And the rock core profile that we obtained back in 1997 is where we got field evidence that the DNAPL phase that probably caused the contamination in the 50s and early 60s has completely dissolved away from the fractures, but is still in the rock adjacent to those fractures and measurable in these concentration profiles, confirming the evolution to the condition on the right-hand side. We used cores along the center line of the plume. Our study site was the northeast plume that goes out the front gate at the property. So this is our detailed study area. You can see in the map view the trajectory of that plume along the red line. And so a vertical cross section running along that line is shown in the upper diagram on the right-hand side, where rock core data taken in the same amount of detail as we saw in that profile is averaged and then interpolated across the length of that plume to give us this concentration distribution that you see. So just like the simulations, the colors represent changes in orders of magnitude and concentration. So we can compare the field data at the top to the simulation at the bottom. And stylistically, these plumes look to be very similar. The warm colors, the oranges and reds represent the highest concentrations. And that's where the bulk of the mass remains today, within a couple hundred meters away from where it went into the subsurface decades ago. So another small detail, what we can do with data like this is estimate the contaminant mass discharge crossing the property boundary at the front gate. And with these data, we've estimated that the current mass discharge is about 2 pounds per year. That's so this mass flux is occurring even though we see that the plume front isn't moving in a measurable way forward and perhaps even appearing to attenuate. So this is the end of my presentation, where I just simply want to remind us the importance of the groundwater flow system and where the groundwater is heading in terms of the seeps and the valleys. And I'm going to turn it over to my colleague, John Cherry, to finish our presentation.
Thanks, Beth. So Dr. Parker explained where the contaminants are located. With minimum migration was a surprise to us when we started our studies. We did not expect to find only localized contaminant migration. So my job here is to explain if this makes sense from a groundwater flow perspective. So as we all know, there's lots of fractures and there's lots of big fractures, but big fractures connect to small fractures. But in general, the speed of flow is generally miles per year. So that's part of the paradox. And as you know, SFL has a high elevation relative to the Simi Valley and Chatsworth. So intuitively, it's reasonable to expect contamination to spread towards the lowlands. And we've got joints, fractures, fissures and faults and earthquakes. And all this gives us the common impression that the contamination should be very widespread. And when we drove up the mountain that day, that's what we expected would be the outcome of our engagement as a panel. So groundwater contamination in the SSFL bedrock presents a paradox. Groundwater flow in the bedrock is fast. The scientific study shows that the bedrock contamination has remained nearly all within the site boundary. A paradox, fast groundwater flow, but very small plumes. Another word for paradox would be conundrum or puzzle. But the point is that the initial impression is an inconsistency of evidence. And that's why so many decades have been spent studying this site. And this represents the groundwater flow part of the story, and all the key components have been studied in detail. The recharge, the discharge, the rock matrix, the fractures, everything that you can measure has been measured in one way or another. So why does the SFL water table level stay high above the surrounding valleys? And when we drove up the mountain that day and we were shown the maps of the water table, we were very surprised. But we were told there were hundreds of wells measuring the water table, so it had to be true. And then the question is, what's the importance of that? And when it rains, the rainwater disappears fast into the subsurface. And this gives the appearance of large recharge, the recharge being the part of the rainfall that actually gets down into the groundwater system. But the average annual recharge is only 4% of the precipitation. And it's a semi-arid climate, relatively dry, not a desert, but relatively dry. The rainfall is small, 18 inches per year on average. So the recharge is 4% of the precipitation, which is basically less than an inch per year. Actually makes its way to the water table, which keeps the water table high. So groundwater from recharge flows downward and outward, some of it ending up at seeps along the valley slopes, and then some of it going deeper. And because recharge is the amount of water going into the system, and it really is the water that drives the entire system, so it's really important. The recharge in this mountain has been studied more than any other mountain in the world. Many papers have been published and many methods have been used. And a published paper then is reviewed by peer reviewers around the world, and then it's published. And if anyone disagrees with the findings, they can write in a letter to the editor, and that gets published. So it's the best we can do in science to make our work out there and to allow people to make criticisms. So most of the rainfall then is lost by evapotranspiration, and by consumption by vegetation. Evapotranspiration returns most of the rainfall to the atmosphere. So after it rains, the water is wet on the rock, and that dries out, and then the vegetation turns some of the water back into the atmosphere. Now, their 4 ponds are used for temporary storage of treated stormwater, as shown here. For the SSFL ponds, water goes in and water goes out, but standing water is uncommon. So there's input and output, but there's not frequent standing water, and therefore there's not much leakage either in up to the atmosphere as transformation, as evaporation, and not much leakage into the ground. So both the total evaporation and infiltration from the ponds are small because there are only a few ponds, and standing water in the ponds is uncommon. And down in the valleys, leading down to the flats, then there are many trees, most of them phreatophytes. Trees are little water pumps, and they do a great job then of returning water to the atmosphere. Professor Becker mentioned Darcy's Law, which is the hydrogeologist's creed, and it's got K, which is the permeability or hydraulic conductivity in it. And in a moment, we'll just take Darcy's Law and we'll stand it on its side. So permeability is the resistance to flow, and it's a measure of the hydraulic conductivity in Darcy's Law. And the permeability then includes the many fractures. So it's a bulk permeability when we're talking about a fractured medium. So we have a puzzle. The rock appears to be very permeable based on large fractures, giving the impression of a large K. But the study shows unexpectedly that the bulk K is not large, but rather it is moderate. So how do we know this? Well, the water table is high. And if the water table is high, then and the recharge is small, then the bulk permeability of the bulk rock of the mountain itself has to be moderate to small. So if we'd have a low water table, then we'd have to conclude that the bulk permeability is higher. If it's a high water table, then it has to be lower. And this is Darcy's Law on the vertical. So basically Darcy's Law is controlled, the level of the water is controlled by the bulk hydraulic conductivity. In other words, the bulk hydraulic conductivity of the rock is like having a spigot on a cylinder where you put water in the top and you control the rate at which it flows out the bottom. by turning the spigot or the tap. So groundwater escapes from the mountain only slowly, and it's slow because of the low hydraulic conductivity of the sandstone. There are shale beds that impede flow, and there are faults that actually impede the flow. And this shows sandstone with a layer of shale in between it. And if the water is trying to get through the shale, then it's restricted in its vertical flow. And if we were to measure water level above that shale bed and below that shale bed, we'd have a big hydraulic differential. As we see with the upper triangle, that's the water level or the hydraulic head, and the lower triangle, indicating then that the shale bed is restricting flow. And we can see this in the field by putting these multi-level devices in, where each one of those dots has a port, and the hydraulic head is measured in the port. And when this was published, and even to this date, this is one of the most detailed head profiles published in the scientific literature. And Dr. Parker has published many of these profiles from Santa Susana and from other sites around the US and Canada. Now, as you know, the Santa Susana has many geological faults. Those are areas where the earth has ruptured. And there have been detailed fault studies because the concern was that these ruptures in the rock would be areas of high flow where the water and the contaminants would escape from the mountain. Just about every type of test you can do to study the transmissivity of these faults has been done. And this is a geological map prepared by Dr. Iden at Stanford and his postdoc Salona. We won't study these in details, but what they show then is when the earth is ruptured, that the shale gets into the faults and tends to seal them. So the faults would be very permeable and would cause water to escape from the mountain if they weren't plugged in a variety of places. And the recharge has been studied in detail on a catchment scale with detailed modeling of the recharge and the groundwater system. And then that information goes into this 3D mountain scale model where recharge is simulated over the entire mountain scale, and that simulates the water then that leaves the mountain. But the volume rate of water leaving the site and carrying contaminants is very small, and we need to think of it in terms of garden hose discharge. So all this water that's carrying contaminants that's leaving the property then can be thought of in terms of gallons per minute. About half of the groundwater escapes from the mountain as seeps and springs. So we generally use the word seep to include springs and seeps. There are no huge seeps on this mountain. They're all relatively small in terms of the term spring. So we've got 165 seeps have been identified and 96 have been sampled. And they all weren't sampled because many of them are basically unsamplable. It's just a little water trickling out on the rock. So everything that can be sampled has been sampled. And here's some examples. When you think of a spring or a seep, you think of water gushing out of rock. But in many cases, it's just a little trickle. And that makes sense because there's not much water going into the system. So the recharge is small, the flow is small, the seeps are small. When it comes to water, everything is slow and small. So have contaminant plumes arrived at seeps? And Beth indicated then on our conceptual model slide that the answer is no. So she showed these deep extensions of contaminated groundwater, but the water that's going directly out to seeps then doesn't carry the contaminants to the seeps. And that's the reason is that the flow of groundwater is so small that the processes that cause natural attenuation have so little contaminant mass to operate on. So they are operating on very little mass, and so the mass doesn't really get to the seeps. So how do we know that faults are not always pathways for contaminants to escape from the mountain? And this just lists the type of studies that we've done here, but they're all consistent. They all provide confidence to the conclusion. And this is the extent of key groundwater contamination in 2022. And when we look at the northeast, at the upper right there, we see that there's just a little snout of contaminated area going off property. And so as hydrogeologists, to quantify this, we say we've got a plume and we draw cross sections down the plume, which is a long sect, and we draw cross sections across these plumes, which are transects. And then we make calculations along the transects as to how much contaminant mass has been carried off. And for that, we need to know the amount of water flowing across the transect, and we need to know the concentrations. And as Beth mentioned, a reasonable estimate is 2.2 pounds per year. And that's an astoundingly small amount of offsite contaminant migration. And the astounding word is being used here because it's what the science shows, and we're quite confident in it. But it was astounding to us, with our initial thought that there's much faster and more voluminous groundwater flow going off-site. And that's part of the paradox then. The scientific answers based on what you measure are not consistent with what your impression might be from what you see. So the paradox, although it appears intuitively that the high-speed groundwater in fractured and faulted rock should have carried contamination significantly off-site, the exceptionally comprehensive scientific study over nearly 3 decades shows that this is not so. And this conclusion has an exceptionally high degree of confidence from all these decades of scientific work and from the consistency in all of the information. So the groundwater speed is large, but the amount of water flowing off the site is small and contains small contaminant mass. Hence, natural attenuation processes can be exceptionally effective because they don't have to operate on much contamination. So as we've indicated here, groundwater from recharge areas flows downward and outward. And if you live in Simi Valley, it's the outward part that you would be concerned about. So we've got these flow arrows, and some of them are deep. And the deep flow discharges beyond the mountain. We don't know exactly where these arrows would go exactly, but it doesn't matter where they go exactly because the amount of water that they carry is so small. Basically, when we crunch our numbers and we take reasonable bounds, the groundwater flowing off-site each year is a drop in the bucket. Now we can calculate a drop and we can calculate a bucket, and this is a pretty small drop in the bucket in comparison to the municipal water supply used in Simi Valley. So it's not scientifically conceivable then that the groundwater contamination from the mountain can have any impact on water in Simi Valley, beneath Simi Valley. So we had the 2009 site conceptual model, which was the basis for Groundwater U. And as you've heard here from Beth and myself, we've gathered much new data since 2009, but no changes have been needed in the SCM in 2024. So did we waste our time? Well, no. All of this new data then goes to a confirmation of the SCM. Now, our overall conclusion then is that the primary action appropriate for SSFL is to ensure that a groundwater monitoring system is put in place to reliably track the contaminant conditions with contingency plans so that if excessive adverse deviations from predicted outcomes arise, you know about it and can react. However, decisions about the groundwater site contamination need to recognize the paradox and be consistent with the scientific evidence. And when we get a few weeks from now to discussing remediation, then this will be the critical point. Thanks for your attention.
Okay.
We've had a lot of great questions tonight, and I want to thank all the participants who put their questions in the chat. And if at any point you feel that when I read your question out loud, that if I got something wrong or something needs clarification, please follow up and just let us know, either in the chat or if you can chime in yourself, please feel free to do so. I'll start off with some of the earlier questions and we'll go from there. This question is from Chuck Rocco, and it pertains to the Brandis site. He asks, The Brandeis site is contaminated far from the Rocketdyne site, and the amount of species of contaminants were sealed by the court. Has your borehole or boreholes probed near the Brandeis site, and what are the findings? So anyone from either the DTSC, Boeing with the NASA team, if you'd like to chime in and take that question, feel free.
Well, I guess I don't mind taking a stab at it, Bill. Mindy or Steve or Tom from DTSC can echo, but there are a number of wells that we monitor on the Brandeis property, and generally speaking, there is no indication of site contaminants from Santa Susana on the Brandeis property based on the wells that we monitor. So I don't know anything about the court document or thing that you mentioned about sealing information. I don't know anything about that, but I can tell you from our program that where we monitor multiple wells off-site, including some on Brandeis property, those wells do not show indications of contaminants from Santa Susana Field Lab.
Yeah, and just to, put a pin in this one, DTSC did an extensive evaluation of the data at Brandeis, and we've done an extensive evaluation of the data at SSFL, and there's no concern for the Brandeis. And I put a link in the Q&A to the fact sheet that was published right after that data evaluation was performed for the Brandeis site.
Thank you. Bill, do we have another question?
Yes, we do. And along that kind of vein of questions regarding offsite contamination and questions for that, we have another one here from Jenny Knack, who's asking, why aren't there more wells dispersed in the southern buffer and offsite? It seems if the well plotting isn't relatively evenly spaced throughout the property, not to mention beyond the site boundary itself, we can't see an accurate representation of what may be going on in the groundwater. So to summarize, with smaller sites, we'll have more evenly spaced wells, typically under ideal conditions. And she's wondering why we don't see more of that across the southern border and in some of the offsite locations.
Well, I can take a stab again. As Beth mentioned, there's over 600 monitoring wells in and around Santa Susana that we monitor on a regular basis, including many in the southern buffer zone. And offsite further to the south in the drainages that lead away from Santa Susana, we've installed seep monitoring wells. We've sampled seeps, in all those drainages around the site, and we see no evidence offsite to the south of site contaminants, nor do we see much in the way of the groundwater plumes extending from the operational areas into the southern buffer zone. So there are plenty of wells there. But based on starting where the contamination is and working our way out, we don't see much at all in the way of contamination in the southern buffer zone.
Yeah,
Dr.
Mike.
Terry and Parker.
To add to that, then, so where there's any evidence that there's contamination in the soil or the subsoil or in the groundwater as a contaminated area or a source zone, then we work our way outward. And we put, in general, wells outward and work inward. So there has to be some evidence of activities causing contamination or a contamination there, then to kind of to justify a study on an area. So it can look like some areas are very low in numbers of wells, but there wouldn't be any reason to put them there. Perhaps, Beth, you've got further comment on that.
I think it's about where operations have occurred.
Yeah.
Thank you. Bill, we'll do one more question and then we'll go to Chin for stakeholders that have hands raised.
Yes, and this is, again, similar in the vein of questions about offsite contamination. This question comes from John Lapper, and he asks, do we know the extent of TCE in groundwater in 1989? My daughters have birth defects from 1990 birth. Let me read this again, I apologize. My daughter's birth defects are from 1999 birth related to the TCE or to TCE known birth defects. That's his question. And I first want to start off in saying, John, I'm sorry to hear about your daughter's health conditions and the challenges your family face. 2 daughters of my own, so I can only imagine how difficult that is. And I want to thank you for sharing that with us tonight. Again, I'll put this question back towards the panel. relating to TCE migration to TCE offsite in 1990 and a potential health hazard or concern from them. So whoever would like to address that, please go ahead.
I'll make a comment. So when a TC moves in the rock, as Beth indicates, it leaves a trail. It leaves diffusion halos. So there's no scientific possibilities for there to be offsite plumes long ago that we wouldn't see the evidence for. So in the early years, the plumes would have had to have been much smaller than we find, 20 or 30 years later. If this were a different type of rock, if it were granite, where you don't have diffusion to the matrix, then we couldn't say that. But the surface water pathway for TCE volatilizes very, very quickly. So although the DNAPL could run down the ground, and the DNAPL could run down a spillway and get into the rock, etc., and that's how much of it did get in the rock, the DNAPL couldn't run off-site. Like it basically evaporates, and that's why you get a fume in a laboratory, and that's why the health hazards on the drums of TC are always about the inhalation and not about the water.
Yeah, and I'll just echo some of the stuff that was presented earlier. There are no off-site water supply wells that have been impacted by site contaminants, including TCE. Nor have there been any seeps that we've measured groundwater contamination with TCE from the site. So, there is no offsite contamination of TCE other than in that one little piece of the plume that Beth showed, and that is not part of the drinking water supply.
Chin, we're gonna go and take some people that have their hands raised. Can you call on our first stakeholder, please?
Yes, thank you, Jamie. We will be taking questions with hand raised in the order that they were raised. The first one is from Daniel Hirsch. Daniel, go ahead and ask your question.
First, I note that DTSC has now admitted what the community has long believed, that DTSC is captured by the polluters it is supposed to regulate. The invitation to the supposed groundwater use sent out by DTSC says, quote, DTSC, in cooperation with the Boeing Company, NASA, and DOE, invite the public to an online groundwater U, end quote. DTSC is cooperating with, rather than regulating, the parties responsible for the SSFL pollution, cutting secret deals with them to let them out of their most basic cleanup obligation, and views the polluters as its partners. Indeed, tonight's PR event, supposedly sponsored by DTSC, features two individuals, Drs. Parker and Sherry, who have apparently long been in Boeing's pay, although in their introductions of themselves tonight, they astonishingly do not explicitly disclose that. There is a long tradition of the tobacco industry hiring people to claim smoking wasn't harmful, the fossil fuel industry hiring people to claim global warming is a myth, and polluters hiring people to claim those industries shouldn't have to clean up their pollution. And the presentations tonight fit the pattern, suggesting that Boeing shouldn't have to clean up its groundwater contamination. To any news media present, we can, upon request, provide a detailed summary of the long ties between Boeing and Drs. Cherry and Parker. So I have a simple question for Drs. Cherry and Parker. When did Boeing start paying you? And roughly how much have they paid you over the years? It appears you began being paid by Boeing roughly 3 decades ago. Is that true? And approximately how much have you received directly and indirectly? It need not be precise, but is it hundreds of dollars, thousands of dollars, or tens of thousands of dollars? And has Boeing also provided additional funding to the programs with which you're associated? And how
15
much?
seconds.
I hope you'll be forthcoming and detailed in your answers.
Okay, I'll speak to this. So Dr. Park and I do research for a number of organizations around the world. Part of this research is funded by the Canadian government, based on it being totally open and unbiased in matching grants. The grant proposals were peer-reviewed by large international committees. The fact that we published in a peer-reviewed literature means we're doing our ethical job as scientists to display this work to the world with everything being open to the public domain. So for you to suggest that money is influencing our science here is basically despicable. And if you don't like our papers and you think our research is biased, then in fact, you can send in letters to the editor with your complaints, or you can get your colleagues to send in letters to the editor. And that's the point of publishing in a peer-reviewed literature. We've given dozens of talks at international conferences and to environmental groups on this. So basically, almost all scientists, I don't know of any who aren't paid to do their science by government or by industry or whatever. So in fact, I challenge you then to get whatever reviewers you want to write scientific criticisms on what we're raising here. Okay, and Beth Parker and I are here because we want the public to have the access to our science the best we can explain it. So there's nothing being hidden here. Of course, we're paid for our consulting, and we're paid by many other organizations around the world, and we're paid by our universities to do this research. In essence, the Canadian federal government is providing research money. And why would they provide research money to go to a site in California? Why would they do that? Canadian tax dollars. They do that because, in fact, they recognize that the value of this research goes far beyond Santa Susana. It goes to Canada and it goes around the world. And of course, that's what universities want their professors to do. Beth, do you want to comment?
No, other than I would just say that I think the issue here, as you've mentioned, John, is for us to use the scientific method to the best of our abilities. And I think we've made a magnanimous effort in the science that you and I have been doing in collaboration with other colleagues at other universities, literally around the globe, has opened up the black box in a level of detail that others before us weren't willing to do. And so I actually think we've done the opposite of what you claim.
Oh, and are you paid? Are you paid for any involvement in all of this? Does being involved on Santa Susana site yield you any income at all? So if we're going to talk about incomes, let it get it all out on the table. But we're not trying to deny income from this project.
I am not paid, but would you please answer the question, how much have you been paid by Boeing? Simple question, disclosure. I have to give a lecture at University of New Mexico in 2 weeks. The first slide is required to be the disclosure of conflicts of interest. You haven't. Tell us how much you've been paid.
I'm sorry. We have talked about the fact that we are funded by Boeing directly as a panel. And we also talked about the fact that we receive money from Boeing as part of our consortium research program, which is matched by the federal government here in Canada. We said that directly and honestly. So whether you understood it or not is not something that I can control completely, but we were very direct about that.
How much have you been paid?
Excuse me, sorry, I'm going to interrupt because we have 40 minutes left and we have 11 more typed questions and we have 9 raised hands. So we can come back to this, but we're going to move on. Thank you for your responses, Dr. Parker and Cherry, and Daniel Hirsch. Thank you for your question.
One more.
Chen, who is our, sorry, go ahead.
All of the acknowledgements in all of our papers, it's indicated where the funding comes from. So Mr. Hirsch maybe should read the odd scientific paper and not speak from such ignorance.
Okay, so thank you for that. Chen, who is our next person with raised hands?
Thank you, Jamie. Next is Christina Walsh.
Yes, hi. Thank you for having this session for Q&A, although I have some serious questions. I'm deeply concerned about the lack of data of the surrounding areas, because if you're only sampling up at the site and not where it comes out based on your own cartoon, as you worded it, I find I've asked this question for 20 years and I continue to get the same answer. The other thing that really bothers me was the question asked by the gentleman about Brandeis. And Mr. Bauer from Boeing said he didn't know anything about that. And the northern buffer zones were created from that litigation. That used to be Brandeis property, and that was taken over as Boeing property so that it could be said that contamination did not go off site. And so for it to be stated that this is not known by Boeing, when it was indeed Boeing that was involved in this litigation and the buffer zones are clearly shown, that is deeply troubling. In addition, when we look at outfall 2, there are seeps that were installed below outfall 2 years ago by you and your staff. I asked for years and years and years, and they pointed across and said, we're sorry, we can't sample down there because that's off-site. And then I learned that where your little sampling wells were indeed still part of Boeing property. So this is sort of a bait and switch, in my opinion. I'm very disappointed. And because my questions have been inconvenient, and no, I have never received $1 from anyone anywhere, but I have been attacked and devoured by Boeing shareholders. And let's remember that a Boeing whistleblower was found dead in his own car because he fell on a gun.
15 seconds.
So please answer my question. Thank you. And I don't want to be banned from the site visit because my question is inconvenient. Thank you.
Thank you, Christina. Who would like to answer that question?
Well, I'm not sure I heard a question there, but you know, all I said was I didn't know about the court ceiling thing that was mentioned. I do know about ground ice wells and what's been sampled there. And Christine, I'll just say simply, we've sampled the water that emerges at seeps off-site where it becomes a spring and continuously feeds Bell Canyon dozens of times over the years, and we do not see any site contamination there. So it has been sampled. We do sample outfall 2. That's been sampled dozens of times over the last several years, with it having rained more in the last couple of years. So, you know, it's been sampled.
Oh, and if I could add, so not only have we sampled seeps, for every seep that you can get water into a bottle reasonably, we've drilled wells at seeps.
What's going on?
And the point was that there's a possibility the contamination could get to a seep and you wouldn't see it in your sample because in fact it would volatilize. And I challenge any of you out there to show me another site anywhere in the world where people have gone to seeps and sampled them and found them to be clean, and then gone to all the bother of carrying through all the poison oak and whatnot, these little drilling machines, to drill down into the rock and see if there's any contamination down in the rock. So in fact, we've had many meetings over these seeps, and we've discussed with the DTSC and you local people about where to drill and all that stuff. We did that for years and years and years, and finally, it was our understanding that we'd sampled or drilled at every site that would make any sense in the scientific context.
Show us the data.
I think it's in the annual reports, the groundwater reports.
It is not. That should be sent to everyone participating here, because I've asked for decades and I don't get those
Wells
answers.
are sampled every quarter. They're in the annual groundwater monitoring reports. They're posted on DTSC's website.
163 million gallons per day is supposed to go down outfall 2 to Bell Creek, and yet Bell Creek is not sampled. Show me data where Bell Creek is sampled, especially when you're talking about pumping down when there was a drought, and now we have quite the opposite of a drought and no new information in the same story. We have glitter all over the hillsides because of the rain that happened a week ago. So to say that these seeps just evaporate is absurd. We all can see that difference. And I'm frankly deeply disappointed to hear this tone still. Like, this is outrageous. And when people like me are silenced for not agreeing and attacked for not agreeing with Boeing, it is really quite evident what the truth is, unless you allow transparency for all of us, including those that disagree with you.
Well, if there's any data that's out there that you don't have access to, then we need to find out about that, and you need to have access to it.
Thank you. Does anyone from DTSC?
Then I request it. Please send it to me, because I've asked.
And I think the numbers that we presented here in terms of the processes for evaporation, evapotranspiration, and recharge are based on measurements at the site. So it's
You're not looking at the seeps where it comes out, though. That's the problem. You're not looking down below off property.
We've looked at 168 seeps off-site, and we've sampled
when they were dry. It was ridiculous.
Christina, I'm gonna see if we can get someone from our team to
I don't think that's true.
to respond to your question. have you typed your question into the chat?
I have not,
Christina?
because I'm trying to pay attention to the presentation, and I
Okay.
expect that should be my prerogative. So I expect a follow-up, because I have been treated like I'm some sort of criminal because I asked the wrong questions. And
No, you're
everybody
not
has
asking
bowed
the
to
wrong
Boeing's
question.
demand that I be banned as a
Christina, I
result
want
that
to make
my
sure that
questions were
Christina,
inconvenient.
I'm going to mute
I
you for
want
just
that.
a second. Christina, I'm muting you for just a second. What I would like for you to please do is, can you please type your question into the Q&A? And I'm going to make
My
sure that
question is much longer.
Christina, please type your question into the chat. I will personally make sure that someone from our team responds to your question, because I want you to get an answer. But because we've cut you off verbally, I want to make sure that the way that you want your question asked is exactly the way you ask it. Please type it into the Q&A, and I will make sure that I personally follow up and make sure it gets answered.
But if I could make one,
Chin, we're gonna take one more question from raised hands, and then we're gonna move back to Bill for Q&A. We have 11 people that have typed questions, and we have 11 raised hands, and we have
Sure.
30 minutes left in the meeting.
Julie Korenstein, go ahead and ask your question.
Thank you. Can you hear me?
Yes.
Yes.
Well, the woman before me, I understand her frustration and aggravation because, you know, we're worried about what is going on in Simi Valley. I happen to live in the Porter Ranch area, but my granddaughter with her husband and a brand new baby have just recently moved to Simi Valley. And so I have often asked similar questions because I'm worried, you know, and I'm obviously not convinced or do not feel comfortable about even the information. And I do appreciate the information that you gave us this evening. I guess my question is, does anyone, and maybe the woman before me had mentioned it, does anyone actually sample or test the drinking water in Simi Valley? I know when I called the Golden State Water District, I believe that's their name, they're East Simi Valley, that's where people get the water from. And, you know, the person said to me, well, you know, if you really want to be safe, make sure that they have bottled water, you know, which did not make me feel very confident. Also, and I don't have all the information that I had several months ago, but the NPDES releases, they are allowed to release water from Santa Susana Field Lab site, and there are certain dates and times that they can do this. It was just, the information was given out about 3 weeks ago, I believe. And I can't remember if they discharge into Arroyo Simi, Bell Canyon. There were 3 different waterways. And does anyone study what actually significantly comes out of the Santa Susana Field Lab into the water they're discharging? You know, I don't think anyone has even mentioned this yet. And also in terms of testing the wells, I had heard several years ago that the Sycamore well in Simi Valley was contaminated, and I don't know if it was closed for a while or what
15
happened.
seconds.
Anyway, my questions are just that even with the information tonight, I have to tell you that I still have the similar concerns and am very worried about their health. Has there been any studies done on cancer in Simi Valley, and especially close to the Santa Susana Field Lab, which would be so important of a study?
Thank you, Julie.
Thank you, Julie. Who would like to answer Julie's question?
I can start. So we have a fact sheet from the Golden State Water Company, and they do test the water in Simi Valley. I'm trying to figure out how to share the link of it with you, but I have not figured that out yet. They provided that to us, so please reach out to them with any questions about the drinking water in Simi Valley. And then there was a second question. Can you repeat your second question, please? The last thing you said? Oh, health studies. It was about
Pardon
the
me?
health studies.
Oh, the health study. Yeah.
Yeah, and DTSC, there have been many health studies in the area surrounding the site, and those are summarized on DTSC's website. And whenever I figure it out, I can put a link to that summary for you also.
Thank you, Mindy. And Julie, if you can just type a really quick question into the Q&A, then Mindy can actually respond to it and put the links in there for you. If you can just type something really short.
Yeah, Jamie, yeah, just the question was some about stormwater discharge from Santa Susana. Just to be clear, we're talking about the groundwater impacts. I know, those are related, but generally, stormwater flows off, and we're regulated at the site through the Los Angeles Regional Water Quality Control Board, and all water that flows off site is monitored under that program, and that's stormwater. And we do capture stormwater, treat it, and discharge it as part of the management of site stormwater, and those data are published on. We can provide you the link, but they're published on a website that for the annual reports that are related to that NIPTES program. The other thing I'll mention is that at the request of the Regional Water Quality Control Board, there was a human health study of the water that flows off-site in stormwater related to Santa Susana, and generally the outcome was that that water is safe in that it's could be ingested and not necessarily safe to drink because of the bacteria you wouldn't want to drink, but it has been studied. That human health study is available on the website as well. We can provide the link to that.
And if I could mention, it's well known across the US and Canada and Europe that almost every community, the size of Simi Valley and larger, and in fact, the community here in Guelph, they all have touches of trichloroethylene or other chlorinated solvents. That's just so common. And the U.S. Geological Survey has done amazing surveys across the U.S. So to find TCE in the geological groundwater beneath a community is just the norm. The concentrations are almost always low, but the fact that there's TCE in any wells at any time in Simi would be no reason at all to think that it comes from Santa Susana after all the studies that Santa Susana have done to look at what's coming off the mountain. So, our whole point of the paradox was if you look at the mountain and you look at TCE in the groundwater there, you would think that TCE beneath Simi Valley could come from the mountain. But the science shows that that's not the source of the Simi Valley TCE. And that's that's very fortunate, and it's also very fortunate that relatively speaking, TCE in Simi Valley groundwater is relatively low.
Chin, let's just take one more question, and then Bill will move on to you.
Sure.
Q&A.
We have Larry Yee. Go ahead and ask your question. You have 2 minutes.
You can hear me now?
Yes.
My name is Larry Yee. I'm the former chair of the Los Angeles Regional Water Quality Control Board, and I was a board member for 10 years until I left in 2022. I'm no stranger to science, having had a career with the University of California, and yet it took me several years to get up the water quality learning curve serving on the regional board. Am I to understand that by conducting these Groundwater U workshops, you believe this will better prepare the lay public to be able to review, understand, and critically analyze the cleanup decision docs or the corrective measure studies that are yet to be issued? I know how technical and complicated these studies will probably be, with tons of detailed data sets and complex information. I can't imagine that you would expect the lay public to be able to have any substantive critique for you to consider. So I know I have a rhetorical question, but why are you even doing these workshops? Aren't your expectations completely unrealistic? So that's a rhetorical question, but I also have a question about PCBs. Before I left the water board, I knew of a water board staff that was studying the level of PCBs in the LA River. and found exceedingly high exceedances at the mouth of the LA River. But she left the water board before she could do any kind of study to find out the source of the PCBs. And we know that PCBs were used extensively at Santa Susana. And I know that PCB or air chlors have been monitored, but not PCB congeners, which are the
15 seconds.
The more serious class of PCBs. So I know, your research has focused on TCEs, but what about PCBs, for instance?
If I could comment on PCBs in groundwater, I published on that many decades ago. But back in the 70s and 80s, PCBs were the big sort of global contaminant of concern. PCBs cling so strongly to any solid surface that, in fact, they never move in groundwater. They're a surface water contaminant. They travel in sediment. They stay in the bottom of lakes and rivers. But PCBs, fortunately, are not a significant groundwater contaminant ever, unless the PCB oil, the DNAPL itself, has gone down into the ground. But even at sites where that is the case, then there's no dissolved plume that comes off of PCB oil. So I guess the end result of all the studies around the world is that PCBs aren't transmitted through groundwater. That doesn't mean that they can't be an issue in any other media, such as surface water and erosion and all of that. But your rhetorical question is an interesting one. People fear groundwater contamination because you can't see it and you can't touch it, and all the data comes from devices put in the ground that you don't understand, and maybe they're in the wrong location and whatnot. So it's a very difficult challenge, I guess, for all of us to somehow speak to the lay public. And Beth and I, and before us, Dave McWhorter, we had hoped that at least showing up to speak to the problem so that you could hear us speak, and basically send in questions or whatnot, would be useful. And also, there's an issue of credibility. Of course, the lay public you're not in any position to judge whether our science is good or bad. So it's the process of the science that we hope that by explaining it, that you'd have some basis for confidence. And the goal here is to have some confidence in something that you're being told scientifically that has to do with the environment. Now, I might mention in my case, I'm the leader of a project called the Groundwater Project, and we publish books free of charge on the web. You can look them up, groundwaterproject.org. And we have increasingly numbers of introductory things on that website, so the lay public, if they want to spend the time, can start studying it.
We have 17 in the queue, but that doesn't include a lot of the questions that I've taken out and responded individually, letting those people know that I'd read the question for them. We probably have close to about 25 to 30. So I'm going to go through some that I think we can answer quickly. One I'm going to read here is from Melissa Bumstead, and she's wondering how many wells are on site and how many are off site. Off the top of my head, I can't quantify all of them, but with all of the off-site and on-site wells and sampling points, we have somewhere in the ballpark of about 600 of them. I can't give you a good breakdown of exactly how many are off-site or on-site, but as you can see, the map that we have right there shows that it's a pretty robust set that we have of different data points in our monitoring program. And if you want to have a really more nitty-gritty or a more detailed kind of view, you can actually go into the groundwater monitoring reports that are provided on our document library. And that does kind of give a breakdown. They have got a lot of really detailed maps on there and some tables if you want to get very specific details. So hopefully that answers your question. And we have another question here from Judy Lance. Has there been any monitoring for contaminants performed in Bell Canyon and especially Bell Creek? Tom Secington from DTSC is a great source of knowledge for the groundwater monitoring happening at the site and all the groundwater sampling that's been conducted. So I open that question either to Tom, but I know we have some experts from NASA and Boeing as well who could probably answer that. Again, the question is, has there been any monitoring for contaminants performed in Bell Canyon and especially Bell Creek?
The short answer is yes. We have some wells that are located in Bell Creek at the headwaters, and there's some seeps and seep wells that are monitored at the top of Bell Canyon, and someone's thrown a slide up that shows them. I guess the ones in the stars are the seeps, and the blues are probably the wells, maybe, or the seep locations, and the stars are the wells.
Stars are the wells. Yeah.
Okay, and there's a couple of more deeper wells that are not shown on that map.
This is the nature of the monitoring network at those seeps in the southwest drainage. So they're cluster wells with multiple completions at different depths.
Yeah, so there's another well that's next to WS 9A that's shown at the top of there, and then there's another well that's below, I think between 882 and SP 22. So we have wells.
To make a comment on seep sampling, we kind of got confused a while ago, but the reason why you sample seeps for contamination at the driest possible period is as soon as it rains or there's any surface runoff, you lose the groundwater evidence. So if we'd done seep sampling after rainfall, then we rightfully could have been accused of biasing the data towards not finding contamination. So we would wait for weeks of dry weather and then just try and get enough water in a bottle. And the effort that the seeps crew put in on this was the most stringent, I think, that's maybe ever been conducted in a situation like this.
And I should add, and just to add a little bit, I actually personally was out there collecting split samples with the geologist out there on all the seeps. So DTSC collected split samples on a high percentage of these seep locations. So there's that check too. I just want to add that that's there too.
Bill, what's our next question?
Yes, and this will be another one that I hope we can answer quickly. This is from Judy Lance. And the question is, since Bell Canyon is in Ventura County, what agency monitors stormwater discharge to Bell Creek?
The entire site is located in Ventura County, but the Los Angeles Regional Water Quality Control Board has jurisdiction, and that's who is in charge of the stormwater monitoring under the NIPD's program for the Santa Susana Field Lab.
And this goes into another question. This one is from Jenny Knack, and she's asking, are there wells below and beyond downstream of the NIPD's outfalls? It seems that there would also be an opportunity for contaminants that are allowed to move offsite at the outfall locations may also have the opportunity to influence groundwater offsite. Is there data for wells that would represent these areas? Are there wells past the NIPD's outfalls? And are we collecting data from them? And do we know if surface water flowing off the site could be impacting the groundwater?
Well, people are thinking of a more direct answer. In general, as you go off the mountain, surface water doesn't become groundwater recharge. Everything starts to discharge. So hydrogeologically, the further you go off-site, the less likely it is to even expect anything to go in the groundwater because the groundwater is upwelling. Okay, and so where you want to look for contamination from surface water is where the surface water is going down into the aquifer. Not that that can't happen locally off-site, but it generally tends to be very, very shallow and unlikely. Now, yeah, I mean, if contaminants are attached to particles and they're eroded and they go off-site, then the particles themselves can carry the contaminants. But chlorinated solvents and perchlorate and all the things we're talking about are not attached to particles that are carried by streams.
This question is from Tom Spooth, and he asks, in this era, we've had a decade of drought rain conditions followed by record high rainfalls. How do these models, the models presented by the Dr. Cherry, Parker, and Manna, how do these models account for the impact of that huge influx of water after such a long dry period?
I'll make a comment and then maybe Fernando and Beth can. So in a dry period, the water levels in the wells gradually go down. And then if it rains a little bit, the water doesn't get to the water table. And when you have really, really rainy period, then the wells start to see it. And all the water levels jump up, and then they gradually go down to where they were. So in fact, the studies of the recharge go over many, many decades in terms of looking at the data. So they're all part of the conceptual model, and parts of that are part of the computer models. Fernando and Beth, you have more comment on this?
No, I think John covered the basics, but yes, just two things, like the way the information we gain from the field are inform these numerical models. It's basically taken into account. So these numerical models simulate both wet and dry periods, therefore simulating the periods of high recharge and the periods of low recharge. And so that's a complex system, and it's complex because it doesn't rain much, as John said. And when it rains, it takes, as Professor Matt Becker explained in session 1, it takes some time before we see a response at the water table. And it is also spatially variable. So we don't see this recharge occurring everywhere. So it's a complex process from a spatial and a temporal perspective.
If this mountain were granite, really hard granite, and the water was flowing into fractures, then when you'd have a big rainfall, you could have a pulse going through the system very quickly. And I think when you see it rain out there and all of the water is running into the fractures, you could get the impression that this would cause a pulse of the plumes discharging, that there could be pulses of contamination coming out the other end of the system. And that's not how a fractured porous sandstone behaves. And this is all part of really what we see intuitively. It rains like mad and the water runs in the fractures and the water levels jump up on the mountain. It could give you the impression that in fact you're pulsing contaminants into the environment down over the slopes, but that's not how the system functions. And all of that's built into our thinking, like it's all built into our models in one way or another. The models can't have everything in them, but they've got bits and pieces in them to the point where we can check them out and I think have confidence in the ultimate reality.
And if I can add just another quick thing. So when you observe these well hydrographs that shows the response to precipitation, sometimes you see these large jumps. But remember what Dr. Parker said initially, the fracture porosity, it's only a small portion of the total porosity. So if you fill that small porosity with water, that will cause the high jump. But that doesn't mean that you have lots of water arriving. It's just that it's flowing through that tiny small part of the entire rock. So that can cause these large peaks in those well hydrographs.
Thank you. We have 9 minutes left in this meeting. Chin, we're going to take raised hands and then we'll try to respond to the typed Q&A while that's happening.
Sure.
Chin, who's our first person?
Thank you. Next in queue is Danny Mulligan.
First of all, thank you. I appreciate your time and your expertise. If there were to be a massive ground earthquake movement, sudden rupture earthquake, would you expect to see any significant change in the release and the further movement of toxins in the plume, as a result of this sudden fault rupture, that would possibly affect the fracture zones and maybe increased compression in the sandstone where there's diffused material that might be squeezed out like a sponge, so to speak, hence further speeding any release or movement of the toxins. Major earthquake, any impact on the movement of these things, either in the fracture zones or in the diffused sandstone, is that?
This is a very good question. I mean, it's an earthquake frequent area, and earthquakes around and about that part of California open up schisms in the rock, and it's been looked at. This issue of does it mobilize the toxins has been studied at a variety of places around the world. But we had Dr. Emily Brodsky at UC Santa Clara look at this, and she's an international recognized expert on what earthquakes do to faults and groundwater systems. And what happens then is that there's a little bit of there can be a little bit of mobilization, but a very short-lived, and very quickly the whole permeability of the system goes back to its original state. So we've talked to the experts about this. We've done our monitoring, and there's no reason to believe then that there's mobilization going on. And then of course we've mapped our plumes. You know, the plumes have been mapped over decades, and that would include the sort of cumulative effect of whatever might be happening through the earthquakes. And I thank you for raising that question, because this is all part of what's unintuitive. Okay, it's unintuitive then that at this site, the contaminants have been so localized on site, and one of the intuitive things that would make a person suspect that the plume should be much larger then would be this earthquake question. And the proof is in the monitoring. Like, with all the coring and all the monitoring and whatnot, the plumes are where they are, and the seeps are clean. At the end of the day, that's the ultimate evidence.
So you might at best see a short pulse during that.
Yeah, it's all short. That's what the scientists conclude.
Well, there's a pulse in the groundwater system, but the movement of the contaminants is attenuated by diffusion and dispersion and so on. So we haven't observed a pulse in the contaminant distribution. What we see is a pulse in the hydraulics of the system.
Right. Thank you.
Michaela, go ahead and ask your question.
My question is, how many groundwater wells are being monitored? What is being monitored to ensure that this contamination does not seep into local groundwaters? Because the site is on a hill, which geographically has seeps and streams, which will seep into the local aquifers and groundwater. What is being done to ensure that the communities are safe and that the contaminants are not leaving the site?
Thank you, Michaela, for your question. Dr. Cherry and Dr. Parker, would you like to answer that?
Well, I mean, your concern is the one that we've mentioned, and it's the paradox. You know, the contamination is up on a hill and people live down below. And it's been indicated there are hundreds and hundreds of wells. But many of the wells aren't still monitored frequently because they're up on the hill and they're contaminated, and they're going to be contaminated for a long time. So the wells that really matter are the wells that are out near the front of the plume. And there's great attention then being paid to what needs to be monitored to make sure that what we're telling you is correct. So,
so the distribution of wells, John, that you're pointing to that are important are the ones that are in the direction of groundwater flow, where these plumes are migrating toward. And equally important to the lateral transport, we want to pay attention to the vertical transport. So one of the reasons we've been putting in these engineered multi-level systems is it allows us to put multiple ports within a single borehole and then monitor the vertical distribution to a point where it's non-detect. And those monitoring points are also helping us to observe whether or not there's movement of these plumes in a downward flow direction, which is also important at the site.
And decisions that are going to be made, you know, by the regulatory agency then on remediation. And along with that will be the final decisions on what the future monitoring needs to be. So my last slide basically indicated that the biggest step in the future as this site gets turned over to future generations is to make sure that the final monitoring network provides the most appropriate assurance that the contaminants are where they are. And if they should ever start to move, we would see the movement.
Thank you. We have one question I want to ask before we move on to our last raised hand. We have a question that came in. It's for Dr. Cherry. And the question says, you noted that your panel was surprised to discover very little offsite migration Were you surprised because previous studies did find offsite migration along fault lines?
I'll respond and then maybe others. We were surprised because we thought that the fractures and the faults and all of that would have provided more avenues for offsite migration. Okay, and that when we drove up the mountain that day, we were surprised. And then we began to get information. We found the water table was shallower than we expected and whatnot. But fault studies were done and hundreds of more monitoring wells were put in so that whatever we were surprised about has been answered. And in some parts of the world, the faults are where the water flows. There are some parts of the world where when people want to drill a well and find lots of water, they drill it in a fault. And then there are other parts of the world where, in fact, that's where you don't find your water is in the faults. And in fact, the bias for the first many years of drilling at Santa Susana was biased towards drilling along faults, along these lineaments that you could see on photographs.
Area photographs.
Yeah.
Thank you. And it's 8 o'clock. We are going to get ready to wrap up the meeting. We're going to take one more question for raised hands. Chin, let's take one last person.
Sure. John Lapper, go ahead and ask your question. Go ahead and ask your question.
Yeah, just a quick follow-up to my earlier question, because I'm understanding what the results are today that you guys are seeing, especially since you came into the project after 2000. But it's hard for me to believe that from the 1950s, and I'll go up to 1990 for my example, where there was little monitoring, little control, little regulations, that you can foresee or forecast that there was millions of gallons of these contaminants and TCE, and that they didn't do harm. That's just what I'm really having a difficult time understanding, because we got our water during my wife's pregnancy in 1989 from the Santa Susana Mill, which is right there on the Pass Road. And they had a water filtering or some kind of system where they got water and they sold bottled water from that facility. And we thought we were doing the right thing and got our water from there. So it's just coincidence, of course, who knows? But I'm just having a real difficult time figuring out where all this contaminant went without doing harm. Thank you.
Well, we, the groundwater panel, our expertise is in groundwater. So the area where we can speak to then is whether the contaminants going into the subsurface have done harm. And coming along 20 years after the main contaminants went into the ground, then it doesn't mean that you've missed anything when it comes to groundwater, because groundwater plumes kind of grow over time. They're like glaciers. In terms of contaminants running off on the surface or anything like that, that's not what we've addressed. And that's got to do with historical operations and all sorts of other things. So that's not an issue then that we would claim to be able to speak to. And I think what you're asking then is a question that's sort of beyond the groundwater pathway issues. Not that you don't have a right to ask a very good question. I'm just saying that if it's a groundwater pathway, then coming along 20 years later, our conclusions are still, I think, very valid because of the way that plumes grow with time. They don't jump out and shrink and jump out and things like that. You don't lose the evidence, particularly in a fractured sandstone, whereas Beth Parker mentioned, everything turns into a diffusion zone that you can then find in your coring.
Thank you. Thank you, Dr. Parker and Dr. Cherry, and thank you, everyone. I want to just thank everyone for their time this evening. I would like to also ask that you please visit the DTSC SSFL meetings webpage to review the presentations or the video recordings for the previous workshops in this series. From the meetings page, you can also register for the third workshop that's happening on April 4th on Zoom, and for the site tour to view groundwater points of interest at the SSFL site on Saturday, April 6th. The deadline to register for the site visit is Friday, March 29th. This slide includes anticipated public comment periods for draft cleanup plan decision documents describing how the responsible parties plan to clean up their areas of responsibility. Each plan will have its own timeline, public notice, and public comment period. These cleanup plans will focus on soil and groundwater cleanup. The first groundwater decision document and public comment period is expected to begin later this year. Please visit the DTSC SSFL web homepage to access site documents, project contact information, submit questions, or to sign up for the SSFL e-list, and for more ways to stay informed and connected. We also encourage you to visit EnviroStore, DTSC's data management system for tracking, cleanup, and more. Please scan the QR code on your screen or enter the URL to access the groundwater survey if you would like to submit additional groundwater questions or topics after this workshop ends this evening. Remember that the survey will remain live throughout the workshop series. Your feedback is valuable. Please take the groundwater feedback survey to submit any feedback for these workshops. You're welcome to take the survey now or wait if you plan to attend the third workshop and the site visit. You can take this survey multiple times. This feedback form will also remain live throughout the workshop series. This slide includes DTSC contact information for SSFL for more ways to stay connected. I will leave this slide up briefly while our technical team members respond to all outstanding questions typed into the Q&A. Thank you to everyone for your time and for your participation. Thank you for our speakers. We also thank you for the participants that asked questions and participated in this meeting. We look forward to seeing you at the third workshop on April 4th and the groundwater site tour on April 6th. You can also re-watch this video. It will be uploaded to our webpage in a week or two. And again, I'm going to leave this slide open while our technical team responds to all outstanding questions. And thank you everyone for your time. And I'm going to turn my camera off, but the meeting's going to stay recording while we answer the questions. Have a good night, everyone. Thank you so much.